We say that a graph G is Eulerian if there exists a closed path on G that uses each edge exactly once. And we want to show that the language of all the graphs that are Eulerian is in P. First, there are a lot of things to precise. Firstly, what is exactly a graph? Well, we say that a graph G basically is just a set of vertices, the set V, or set of nodes, that are connected with edges. And so, for example, this is a graph. This is a graph too, and a single node is also just a graph. Anything that is just a set of points, nodes, vertices, how you call them, that are linked with some edges or not, is called a graph. Okay, and so what exactly is a Eulerian graph? Well, we say that a graph G is Eulerian if there exists a closed path. So just you start from a vertex and you want to come back to this vertex only using edges. And one way of doing it would be starting from here, going there, and then coming back here, and then coming back here. It's always possible to go back to the same vertex. But here we want that the graph was Eulerian, meaning that there exists a closed path, but that uses each edge exactly once. So here it would be impossible, because if you have the same graph here, and you start from any vertex, let's say for example here, you need to go there, and then you would go there, but then you would be stuck because you already used this edge and this edge, but you didn't come back to the initial vertex. And so here you're stuck. And so the language that we want to study is the language of all graphs that are Eulerian. And so here there is something else also to precise. What is exactly this notation with the angles here? This G in some brackets. It basically means that it's a binary encoding of the graph G, because we know that we are studying here a language and thus we are studying problems, and we want to study problems that take an input that is a binary string and that outputs either no or yes. And so the encoding of G could be anything that you want. One encoding that I can imagine would be, for example, just if we have n vertices, then the encoding could simply be a n by n matrix. A matrix can be simply then transformed as an n squared string, such that the ijth element of the matrix is equal to 1 if and only if there exists an edge ij that belongs to the set of edges. And we write it like this, that the pair ij belongs to E. And the last thing that we want to precise is also, we want to prove that the language is in P, so that there exists a Turing machine that solves this problem. If you receive a graph as an input, or its binary encoding, well, you want to be able to output, yes, it is Eulerian, or no, it is not Eulerian in polynomial time. And so here, what is the size of the input? Well, we can say that the size of the input, so here, let's say the size of G, or more precisely the size of the encoding of G, is something of at most the number of vertices plus the number of edges. And no matter how you choose your encoding, as long as it is smart enough, you will always be able to find an encoding in such way. And so we want to find an algorithm that solves this problem in polynomial time of this quantity. So let's start. When you have such problems, the first thing is always to see in practice when is the graph Eulerian or when it is not. For example, let's draw a graph here that has only 4 vertices and 4 edges. And so here, is this graph Eulerian? Well, yes, because no matter where you start, for example, if I start here, I can go there, go there, go there, and go there, and then I will have my cycle, my closed path, that uses each edge exactly once. So this graph is Eulerian. Now let's take the triangle graph, like this. Is this graph Eulerian? Well, if you start here, then you have to go here, here, and here, and again, it works. But now let's, for example, take this graph. Now, no matter where you start, it will be impossible to find a Eulerian path, because if you start from here, then you will have to go here. Maybe you want to go there, and then it's impossible to come back to the first vertex. And also, you didn't cover this edge. And so, for example, if you go now here instead, then you would have the same problem. And so this graph here doesn't work. Let's try to find other examples of situation when it doesn't work. Let's try to draw this graph here. But again, it doesn't work because if you start from here, you could go there, there, and there, but you wouldn't cover this edge. So you can try to go there, and here you wouldn't cover this edge and you wouldn't find a cycle, a closed path. And so now, what do these graphs have in common and what do these graphs have in common? Well, we can try to think a bit and we can see that here each vertex has here two edges going from it, and here also two edges going from it. And here this node has three edges, this one has one, this one has one, this one has one, this one has two edges, three edges, and one edge. And so what we can imagine is that if we want to not have problems, if we want to not get stuck, well, we need each time that we visit a vertex to have, let's say, a way in and a way out. So we want always to have an even number of edges that go out from this vertex. We say that the number of edges that touches this vertex is the degree of this vertex v. And so when we are coming to this vertex, we want to be always able to go out from this vertex without getting stuck. And if we had, let's say, another edge here, well, here we can the first time come in and then come out, but the next time that you will come in, well, you will be stuck because all the other edges will be already taken. And so you want to have an even number. You want to have a pair of coming in and coming out edge. So here, if you come from here, you would just have to go there. And so this idea shows that if you have a vertex that has an odd degree, well, it's kind of impossible that the graph will be Eulerian because, for example, let's say that we want to cover each single edge and we have a vertex here that has an odd degree. And so here, we want to cover all the edges. So let's say we start with this one, then we go out, we can go out by this one. But then it will be impossible to cover this edge because if we enter from here, well, it will be impossible to go out. You will be stuck here. And sure, we have, let's say, a starting node and an ending node. And so we could think that maybe in this situation it is allowed. But no, because even in the starting node or the ending node, which are the same node actually, well, you will always have, because you have a cycle, you will always start also from one edge and then you will have, at some point you will have to come back to this vertex using some edge, for example, this one, but this one will still be uncovered. And so you would have to take it and then you are stuck because it will be impossible to come back to this vertex. And so we can show the first thing is that if there exists a vertex v, such that the degree of v that we write like this is odd, then G doesn't belong to our language L. That L here is just the language Eulerian-Graph. And so it could be nice to prove this direction too, because if we prove it, well, it would mean that we just need to check that all the vertices in the graph have an even degree. And we can do this in polynomial time because we just need to check every vertex, check its neighbors, and check if there is an even number of them. If it's true, how to prove the converse direction? Well, it's a bit more technical. We want to prove that if for all v in my set of vertices, then the degree of v is even, then G belongs to our language. And so let's assume that we have a graph that respects this condition. How to prove it? The idea comes from, in such graphs, no matter how the graph looks like, as long as the degree is even, so if you have here, well, no matter where you start, you will always be able to create a cycle. So here, if you start from here, because we will never get stuck inside of a vertex, because we always have a way in and a way out, it will always be possible that at some point we can come back to this vertex. For example, we can start at this vertex, we go there, then we could go there, and then going there. There is always such a way, because no matter where you start, you will always have an edge available here, and no matter where you go, you will always have a way out. And so you will always be able to come back here. But as we drew here, this set of edges, this path, is not a Eulerian path because you want to visit all the edges, and this one, and this one are not visited. And so we can think, okay, but because these edges are not visited, it must be that at least one of these vertices has unused edges. Because, okay, this one, we used all its edges. This one too. But this one, we didn't use this one and this one. And because we didn't use all the edges in the graph, there is at least one vertex that has unused edges. And so we can now choose, let's say, now I want to start here and I want to create a cycle here. And because each vertex of the graph has initially an even number of neighbors, well, we can just remove these edges and be like, okay, now I want to create a cycle from this vertex. And because an even number minus an even number still is an even number, the remaining here subgraph is still a graph such that each vertex has an even degree. And so what we can do is simply to repeat the process and to be like, okay, now I want to create again a cycle that uses each edge at most once. And so we can always do it by just traveling the vertices. I can start from here, then I can go there, and then I can go there, and then I can go there. And now if all the edges are covered, we can just stop, and the final path will just, let's say, merge the two cycles, because we can start here, go there, and now instead of going there, we continue with this cycle. So we can go there, go there, go there, and then go there. But in the case, for example, I don't know, more unused edges, let's say that the graph was like this, then I would again have another vertex that has unused edges, this one, and I can continue the process until at some point all the edges will be covered, because each new cycle uses at least one more edge. And so because the number of edges is finite, well, at some point you will be able to merge all these cycles into a big Eulerian path. And so with this method, we can prove that indeed, if our graph has all vertices with an even degree, well, we just show that there is a path. There is a path that uses exactly each edge once and comes back to the initial vertex. And so we prove this. And now, because in the earlier part we proved this direction, we have the equivalence. And so basically, the Eulerian-Graph language is the same language as the language even degree, that is all the graphs such that for all v in the set of vertices, then the degree of v is even. And so this is equivalent to our initial language. And checking this, well, it's indeed in polynomial time. We just have to check each single vertex, check its neighbors, count them, and this takes, of course, at most the number of edges in the graph. And so for each vertex, we will compute its number of neighbors and check if it is even or not. And if at the end of the process, we just have that all the degrees are even, then we accept, and if not, we reject. And so we can bound this process by simply, we said that for each vertex, we need to check at most the number of edges. And so this is indeed polynomial in our initial input size.